okay? So now let's finally get to the energy method, okay? And let's, for starters, we've been doing most everything on unbounded domains, okay? We're going to jump over to a bounded domain first, okay? And we're going to eventually take A to negative infinity and B to positive infinity, okay? Concepts are easier on a bounded domain. And so that's a good place to start, okay? Well, in this case, we haven't shown how to get a solution. We'll talk more about that when we get to separation of variables. But assuming that we do have a solution, can we show that it's unique? Okay. Well, in this case, again, the idea with energy functions is that we want to do something like integrate against our PDE. Okay. And this time we're going to integrate with respect against the unknown function itself, u. So that if I differentiate this expression now, or this formula with respect to, or sorry, if I integrate these integrands with respect to this integrand with respect to t, right? I see that this integrand here is the result of a differentiation of u squared over 2 with respect to t, okay? So I can change this into a derivative with respect to t of u squared over 2. I can use integration by parts to rewrite the thing on the right as k u ux, evaluated from x equals a up to b, minus k integral from a up to b of ux squared dx, okay? So what does this give me so far? Well, if I define an energy now, so E of t is equal to just the integral from a to b of u squared over 2 dx. Let's say that's my energy functional, right? It doesn't have to mean something physical. Remember, the energy functional is just motivated by the fact that sometimes these objects are physical in meaning. And so I want to come up with a functional that'll take some usually even function of my solution and return just a scalar quantity in time, okay? Well, so if I define E this way as the thing that I found I could write the time derivative for in terms of some other expression in terms of x, okay, of u, which seems promising, okay? Then, okay, what I know is that E prime of t is less than 0. Why? Well, because this thing here, okay, is less than or equal to 0, okay? But I have to put a condition where it'll be less than or equal to 0 as long as this boundary term is itself less than or equal to 0, okay? And how does that come about? Well, that's going to come about if u or ux is equal to 0, okay, at x is equal to a b, right? So there's several situations that could happen here, right? You could have that u is 0 at x equals a, and u sub x is 0 at b, okay? You could have that u sub x is 0 at a and b. You could have that u is 0 at b, and then u sub x is 0 at a, right? So you can have all these sort of mixed conditions. And so what we'll show sort of applies to multiple cases, right? Both the Dirichlet and the Neumann cases of these initial boundary value problems for the wave, okay? So, for example, this will work for, homogeneous boundary conditions, right? So then in that case, E of t is less than or equal to 0, right? Because in the case that E of 0 is equivalent to 0, okay? This would imply then that the integral from a to b of u squared xt dx, right, is less than or equal to the integral just at time equals 0, okay? Basically for all t greater than 0, okay? So, so sorry, excuse me. So let me back up. So essentially, you don't even need this condition here. So the condition E prime is less than or equal to 0 implies that this integral here is going to be less than or equal to the integral that you would have taken at t equals 0. Excuse me. Okay, so fine. So what does that do for us? Okay, well, it allows us to derive a theorem, okay? And we'll just do this in the case of Dirichlet boundary conditions for now. It states that if U solves the following initial boundary value problem, okay? And we'll make it fairly general. U sub t equals k uxx plus f of xt, right? We haven't even really talked about how to solve inhomogeneous problems yet, but just assume that we have some way of getting a solution, or we know about the existence of solutions. If u of 0t satisfies some, it could be even be, you know, a function of time. U of lt is some function of time, and u of x0 is some function of space, okay? Okay, so that's our initial boundary value problem, okay? If this is true, then U is unique. That's it, okay? Now, I need a few things, right? So I need that G is continuous, right? And bounded, okay? But other than that, I think I have everything I need, right? So how do we proceed with this? Well, we sort of follow the logic of the case of wave equation energy function arguments, okay? The idea is that if you wanted you to both solve the IBVP, then we'll define this function W, U1 minus U2, which solves the following initial boundary value problem, right? So if I take, right, W sub t, I get U1t minus U2t. That's equal to k U1xx minus k U2xx plus f minus f. So our f's cancel, and we're just left with k wxx, right? W at 0t is equal to U1 at 0t minus U2 at 0t. That's equal to A of t minus A of t, which is equal to 0, right? WL of t by similar logic is equal to 0. And also W x of 0, by similar logic, it is equivalently 0. Okay? So this is now our new initial boundary value problem. It's just the heat equation with homogeneous boundary conditions and a homogeneous initial condition. Okay? So now what I'm going to do is I'm going to define E of t is equal to the integral from 0 to L, w squared over 2 dx. Okay? And basically by the arguments that I've made above, right, I won't go through them again because they would be exactly the same. The integral from 0 to L of w squared xt dx is less than or equal to the integral from 0 to L of w squared x 0 dx, okay? But what is w of x0 but just, right, 0? So it's just the integral of 0 now. So I get that the integral from 0 to L of w squared x t dx is less than or equal to 0. Okay. Now this thing, right, not only does it need to be less than or equal to 0, it needs to be greater than or equal to 0 because it's some, function squared. Okay. Also, because it's a solution to heat equation, it should be continuously differentiable, right? So that means that it has to be 0 everywhere, basically, and x is in 0 to L and t greater than 0. Okay, so this implies that U1 is equal to U2, basically wherever x is from 0 to L and t is greater than 0. Okay, so that's uniqueness, right? So that works out in the case of homogeneous Dirichlet boundary condition problem. You can show something similar, okay, for basically for Neumann and basically mixed boundary conditions, right? So like a mixed boundary condition would be that u at 0t equals so many of t, and u sub x L t is equal to some b of t, right? That'll work as well because you get that you'll get that cancellation with the boundary conditions, right? You go back to here. And in that case, everything still cancels out all right on that boundary term. Okay? So that's the idea, okay, on a bounded domain, okay?